methodological advances in robust optimization. Optimization. This year's award winners, Dr. Arkady Nemirovsky, Georgia Institute of Technology, and Dr. Yuri Nestorov, Université Catholique de Louvain in Belgium, for their seminal work in convex optimization theory, including the theory of Dr. Action Committee for the World.
Good morning, everyone. Welcome back. Before we get started about the lecture, let's watch a short video. This is a prize announcing by Michael Jordan. It's about they give two prizes in this prestigious award. So they give one for computer science and mathematics. The other is for life sciences, like biology. And as you know, Michael Jordan is one of the leading mind in computer science, and he's the committee chair for this award. And this year the award is given. So this is called WA. It's a new award started by a hedge fund in China. And this year they give two mathematicians, especially in optimization. It's Nemirovsky and Nestorov, the two guys we mentioned that are giants in our time. And Nestorov is the author of our textbook, one of the textbooks, the yellow one, lectures on convex optimization. So they share the prize is like 10 million Chinese yuan, and it's about 1.5 million US dollars. So it's a big prize. Let's watch the short video about the prize, why they got the prize, and how optimization is useful in our society.
Laureate Association Prize in Computer Science or Mathematics. I am honored to announce this year's award winners, Dr. Arkady Nemirovsky, Georgia Institute of Technology, and Dr. Yuri Nestorov, Université Catholique de Louvain in Belgium, for their seminal work in convex optimization theory, including the theory of self-concordant functions and interior point methods, a complexity theory of optimization, accelerated gradient methods, and methodological advances in robust optimization. Optimization theory is arguably the area of mathematics that has had the most significant impact outside of mathematics over the past 3 decades. Optimization theory has found major applications in fields such as control systems, economics, signal processing, machine learning, resource allocation, energy management, supply chain management, and finance. In many of these fields, it has provided both conceptual foundations and the basis for the design of practical algorithms and real-world application. Dr. Arkady Nemirovsky and Dr. Yuri Nestorov have been leading researchers in optimization theory during this fertile period. Their work has sparked the first-order revolution that has allowed optimization algorithms to be applied to the large-scale problems characterized of modern applications. Their work has also driven the development of new computing platforms to support these algorithms. Their development of a complexity theory for optimization and a suite of acceleration methods has deepened our understanding of what is possible in optimization and what is meant by an optimal way to optimize. Their development of robust optimization and stochastic optimization methods has been critical in fields such as control theory and statistics. The development of a theory of interior point algorithms was Nemirovsky and Nestorov's early crowning achievement. Their theory isolated a fundamental property known as self-concordance that makes interior point algorithms so efficient. The conceptual advance was enormous. They showed how several hundred complicated algorithms with complicated proofs and little apparent connection can be described in a simple and elegant framework. Moreover, they were able to extend many previous known interior point methods to cover a vastly larger range of problems than just traditional linear programs and quadratic programs. Before their work, it seemed possible or even likely that the great efficiency of interior point algorithms relied on some special feature of linear or quadratic programs. But the framework and analysis of Nemirovsky and Nesterov made very clear what problems the algorithms could be extended to, and moreover, what the extensions were. A particularly important extension is known as semi-definite programming. It has become widely used in computer science as a relaxation method for solving discrete and difficult combinatorial problems. Nemirovsky's development with Yudin of the information-based complexity theory of optimization provided an additional essential link between optimization and theoretical computer science. It provided lower bounds on the rate with which any algorithm based on certain primitives can optimize functions in a certain class. An early application of the general framework was to the problem of optimizing a smooth convex function using gradients of the function. Nemirovsky's framework revealed a lower bound that was faster than the classical steepest descent algorithm, which naively seemed to be the most efficient way to make use of gradients in optimization. Nesterov resolved the conundrum by developing a new family of algorithms, the accelerated gradient methods, that were provably faster than steepest descent. Moreover, these algorithms attained Nemirovsky's lower bound. This entire line of work has been exceedingly insightful and productive, yielding a range of benchmark rates and optimal algorithms for attaining those rates in a range of problems. Finally, it is important to note that Nemirovsky and Nesterov have written several textbooks that have brought their discoveries and perspectives to a wide audience in mathematics, engineering, and beyond.
Okay, so with this, I think it's a better motivation than that I gave in the beginning. So if you work really hard in optimization, you can get maybe $1 million by yourself. Okay, so let's continue in constraint optimization. So our goal is to solve an optimization over closed convex set Q, and suppose F is mu strongly convex and the set Q is closed and convex. And then there exists a unique solution. This will be a homework problem in problem set 1, and problem set 1 has been released. You can check it online. It will be due in 2 weeks from now, so next Thursday before the class. You need to submit your homework. And you need to submit just one PDF containing all the theoretical solutions with some other code files. These are just simple implementation of the projection we are going to talk about. And if you can, please write in LaTeX, or at least just type it, because it's easy for grading the theoretical problems. Okay, now let's see how to solve such a problem using the idea of gradient method. So from now on, let's define the projection operator. Suppose this is my set Q, and here's a point outside the set Q. This is x0. I want to find my projection, an orthogonal projection from x0 onto the set Q. So this will be the closest point to x in L2 norm sense. So if you write, if you draw a tangent line, this will be a rectangle. It's perpendicular to the tangent line. Drawing here is not that good, but that's the idea. Well, if x0 is inside the Q, then the projection is at x0 itself, if this is x0. The reason why we need projection here is because suppose this is your set point xk, and if you want to take a gradient step going along the negative gradient direction with this long, suppose this is your step size h, and now you are at xk plus 1. Because the minimization is constrained with respect to this set, so you want to return a point within the set with the smallest function value. But this point is beyond the set, so I want to take one step back, and the easiest way is just project back onto the set. That's why we need this projection operator. There are a few properties of the projection operator, and there will be problems in the problem set 1. Let's just list a few of them that will be needed in our discussion today. This slide might say that projection operator is in some sense non-expensive. If you do projection onto x1 and x2, compare the difference between the two, then this is normal than the distance between the 2 points. So it's like this is x. Suppose this is the point x and have another point y. Here, I'm sorry. I'm assuming Q is closed and convex. This is my point y, and this is the projection of y, projection of x. So this distance is no more than this distance. The theorem is saying that suppose x star is an optimal solution to the constraint problem, and if we take a gradient step, no matter how long the subset h is, if you take a projection of this, the one after gradient step, then you project back onto the point x star. So suppose this is your x star, and you go along this negative gradient direction. No matter how far you go, if you take projection, it will always project back to the same point. These are some homework problems. And there are several other properties of the projection operators that you need to show, and all of them are mainly based on the definition, which is also equivalent to this argmean. Argmean here means the minimizer. Mean just means the function value. Argmean means the minimizer. You need to return which x achieves the minimum. And so these two are equivalent because we are only caring about the minimizer, not the optimal solution. So they are the same. Well, this one is more useful than this definition because this is a one strongly convex function. And also it's one smooth. The condition number of kappa is just 1 here. So it's a very well conditioned function. You can either use strong complexity. We have all these inequalities for strong complexity and also the properties for smoothness function. So you have many inequalities, many lemmas, theorems to use.
Is it norm 1 over there?
These are all 2.
That's 2 as well.
Yeah, all of them are 2. Okay, now let's see some examples of projection. The first one is negative orthant. It's just so this means all the coordinates are negative, right? So it's just the first orthant. The projection for this one you just take the maximum of 0 and your coordinate wisely, right? So for each coordinate xi, this output is just the max of xi and 0. Okay. Second one is a box constraint. Box constraint is like a cube. So you constrain the lower bound and upper bound of each coordinate. So this L is a vector, U is a vector, and so basically your constraint looks like this. Your xi is between upper bound ui and lower bound li, and the projection here. For each coordinate, you need to make sure the output is no less than li and no more than ui. This is just a hyperplane, right? Affine site. And the projection. To get a projection, this is the same as solving the least square problem. So the projection is x minus E transpose. This is about just the L2, about defined in L2 norm, and the center is C, the radius is R.
Professor, I just have one question about the affine set. So what happens if AA transpose isn't invertible? So, so for instance, if one of your constraints is AX equals 0 for one particular dimension, or AXI.
Then I guess you have some redundant
Okay.
constraint, and you can eliminate them.
Okay, that makes more sense. Yeah, sorry, that was a stupid question.
Yeah, no problem. In linear programming, so this is one of the typical constraints in linear programming, and if you have an if some of the constraint is a linear combination of others, you can always limit them to reduce the number of constraints and make the solution the solving easier. The formula looks quite complicated, but the idea is very simple. If x is outside, then you just connect. This is the ball with radius r. This is center C. If x is outside of the ball, you just connect, draw this line between C and x, and compute this point. Otherwise, the projection is just x itself inside the ball. This is a half space. So this is a linear inequality in X. It's just describing a half space. These are some simple sets Q and what their projection operators look like. And I think in problem 3, you need to implement the 5 operators. These are quite easy to implement, and you need to test whether a projection operator is implemented correctly. The way to test is like, suppose you have a set, maybe the box. Suppose have a box, you need to give the L and the U. You can just generate some random number of maybe 0, 1. And you need to generate some random points or just pick some points, maybe the origin or one vector or whatever you want to choose. Suppose there is the point, there is the box, and you want to test whether the projection is correct. Then you apply your code on this point, right? Then you have a projection. Then you just check if your point satisfies all the constraints here, whether it satisfies all these constraints. You need to test at least 3 points and then report whether the projection operator is functioning correctly. Okay, I think now we are ready to do the convergence analysis of the gradient method for the projection, for the constraint optimization. Yeah, I shouldn't erase this part, but these are the results we are going to use. By simple, I mean the projection onto the set Q is easy and it's available to us. So this is gradient method for a simple set. The algorithm is the same as the gradient method for unconstrained problem, except we have a projection here. After you do the gradient step, you need to project so that the xk plus 1 is still in the set Q. This is kappa. All these are condition numbers, kappa.
Should that be kappa minus 1 over kappa
Yes.
plus 1 or?
Sorry. That's right. Yeah. The statement is pretty much like the one we had for the strongly convex when for the strongly convex function when we are solving unconstrained optimization. So we always begin with the definition RK. So as before, we compute what RK plus 1 is, and the square of RK plus 1, by definition, so it's xk plus 1 minus x star. Xk plus 1 is this projection, and x star is equal to this projection due to the theorem we just gave. And according to the lemma, the projection operator is non-expansive. So the distance between these two projections is normal than the distance between these two points, right? And this is the difference, the two. Take the square. And then the square of this one is RK plus RK square. And they just expanded the quadratic term. Okay. Recall that we had a lemma for strongly convex, near-strongly convex, and L-smooth function f. You can say that for any 2 points x and y, this is a lemma we stated last time. So now let's use this lemma to here. Taking x to be xk, taking y to be x star. So we can continue the inequality. Okay, this is just some algebra. So first of all, it's this inequality and also the choice of h is in this interval. So this term here is non-negative. Sorry, it's non-positive, and hence rk plus 1 is normal than rk. So rk is again a non-increasing sequence as before. And also we have a contraction factor. This is smaller than 1. So rk plus 1 is strictly smaller than rk. And also recall we had a lemma last time. This is also one of the problems in the problem set 1. So if function f is mu strongly convex, then we have this inequality. And applying this inequality here, we can further continue this one. This one simplifies to 1 minus mu h squared. And hence we have the first statement proved if you apply that inequality recursively. Right, this is a recursive formula between rk plus 1 and rk. Apply that one repeatedly, you get this one. Right, and the second one, so it's from here to here. Just take h to be 2 over mu plus l and use the definition kappa is l over mu. So you can directly prove the second one. The last one is as before. So you have the result between, for distance xk minus x star, right? You have the result in terms of this. And now we want to turn the distance into the function value. Because function f is L smooth, so you can use the smoothness property to do this transformation. And this is also a similar idea as what we did for the unconstrained case. So these two are similar proofs, so I will just omit them. Any questions?
How did you get the idea of this inequality at the first place?
This one?
Yeah.
The intuition is because it's strongly convex. If it's not strongly convex, for example, if you take mu to be 0 here, you have no contraction factor. You just have rk plus 1 is less than or equal to rk. But with strong convexity, you can always say something wrong. And so now you have a contraction factor. And this gives you the linear convergence rate. Remember, this is linear convergence. And if you don't have this one, that is in the convex case, you just have sublinear convergence rate. So for strongly convex, you always expect to have something like this. Rk plus 1 is smaller than a factor times rk. And you always want to build something to make this show up. Okay. And now let's move on to the non-smooth optimization. What we discussed previously was mainly about smooth optimization, either constrained or unconstrained. we always work with gradient f of x. And now we are going to change the subject to the subgradient, that is for non-smooth optimization. When the function f is non-smooth. We define a subgradient vector to be a vector satisfying this inequality. Then we say this vector G is a subgradient of the function f at the point x. So for a smooth function, pick any point, you have a gradient. This gradient f of x is your G, and it's unique at any point because it's smooth. Well, for a non-smooth function, this is like the absolute value function. At this point, your derivative is just -1. So G here is -1. At the point on the right-hand side, so G is always 1. But at this point, you have multiple choices. G can be anything belong to the interval -1 to 1. Because if you draw any line, it's underneath the function. This inequality is just describing this fact. If you define a linear function in y along this direction, this is like the slope, g0 slope. Right? You can take any g to be the slope, and the linear function is always below the function f. And we use the notation f prime of x to denote the subgradient f at g. In this case, we have multiple choices for G, and we do have a name for this set for all the possible subgradients, and it's called subdifferential. Subdifferential is denoted by partial f of x, and it's just the set of all the vectors G such that this inequality is true for any y. So here, we have two claims. Claim 1 is when function f is convex, then your subdifferential set at any point is then empty. Right? If your function is if your function f is convex, then you can always find the subgradient, which is the gradient. No matter smooth or non-smooth, you can always find the subgradient. It's always existent. And second, if f is smooth, f is convex and smooth, then the subdifferential degenerates to just a singleton, just the gradient. There are two major differences between subgradient method and the gradient method. In gradient method, the basic step is xk plus 1 is xk, considering the unconstrained case. Right, and the simplest subgradient method, we just replace the gradient by the subgradient. But the performance of the two methods are quite different. First of all, along the negative gradient direction, you can guarantee the function value will decrease. This is what we have shown. Both the function value and the distance, this rk, they both decrease, right? But along the negative subgradient direction, you cannot guarantee the function value decrease. This is a major difference. So that's why gradient method is always called, usually called gradient descent, because you can guarantee descent property along the negative gradient direction. But for subgradient, if you call subgradient descent, then this is not precise, because along the negative subgradient direction, you cannot guarantee descent property. So we cannot guarantee, this doesn't mean k plus 1. But for this one, for the gradient method, this is true. And another difference is for unconstrained case, if you use gradient method, the optimality condition is when you can find a point x such that gradient is 0. But in subgradient method, if you are only looking for a point such that the subgradient is 0, then this is not good enough. Because if you suppose we want to solve this absolute value function, and no matter which point you begin, either this side or this side, then subgradient is always constant, either -1 or +1. Or if you jump to this side, you jump from +1 to -1, but you never find 0. 0 is only here. And you can never achieve this because this is the optimal solution. This is this is some ideal solution, right? You can never achieve it numerically. If you run an algorithm, you can never reach the point. You will always be in an epsilon region, right? You will be just closer to it, but you can never reach it. So we will never find the point returns your subgradient with 0 value. So the method will never finish in practice. So the two main ideas in gradient methods do not work. Either the descent property doesn't work, or the optimality condition doesn't work. So that subgradient does provide some good property. That is the definition there. It's this one. This is the subgradient inequality. So with this inequality, let's try to see what property the method or subgradient can provide to us. Let's fix x star to be an optimal solution. so since we just talked about constraint optimization, let's again consider constraint optimization. Q is again convex and closed, but the function f now is just convex and not smooth. It's not smooth anymore. Considering a function with which is not smooth and it has the first order oracle as the subgradient. So we will fix f prime of x. Even though this one you have multiple choices, but in the algorithm we want to always fix it, make it deterministic, meaning that if you call this oracle twice, it will return you the same thing. It will not be different. Okay, so now let's fix x star to be an optimal solution to the constraint problem. And plug this point into the subgradient inequality. Okay, so by subgradient inequality, we have this one. And also noticing that f star is smaller than or equal to any f of x. So putting this one to the left, we can say that right. So this gives a way to characterize where the subgradient, the optimal solution should be. Right? Suppose this is suppose this is my subgradient direction, and this is a hyperplane at the point x. Then my solution, optimal solution, x star, should be on this side, but not this side, right? Because this is a vector, x star minus x is this vector, and this is my subgradient direction. The inner product of the two is less than or equal to 0. So pictorially, the point should be a point on this side, not on the other side, right? It should be in this half space. So this means my x star must be in this half space. So this is with one point. So suppose we have one point x. This may be your search point. Let's say x1 or x0, your initial point x0. With x0, you can locate your point x star on this side. What if we have another point, maybe with some algorithm, for example, the subgradient method, you have another search point, x1. This is your point x1, and this direction is the fx1, the subgradient at x1, right? So it's the same argument. We can locate the point x star on this side, right? So it must be in this intersection of the two half spaces. As the algorithm proceeds, you have more and more points, right? You can have more and more half spaces. So your point will be in a smaller and smaller localization site. So we define a localization site. This is just formalizing the statement, the description we have here, right? So we can say X star must be in SK. And also SK plus 1 is contained in XK. It's getting smaller and smaller. We are shrinking the size of XK.
So F has to be convex, right? Still.
Yes, yeah. Same assumption as before. The idea here is to make the localization site smaller and smaller as you have more and more set points or half spaces. It will be smaller, smaller. Right? You can even have something like this. So you can make it smaller and smaller. And then the question is how small this site will be. Because the smaller the site is, then we are more certain about where the point X star is located at. And also this localization idea is the key idea in many non-smooth optimization algorithms. For example, in the cutting plane method or center of gravity or even the ellipsoid method. In all these methods, the localization idea is the key. So we always want to find a smaller and smaller set so that we can know where the point X star is. And also we need to have a way to characterize how small this set is. And this will always give us the convergence rate. To describe how small the localization site is, we need to define another notion. for any point x star, a fixed point x bar, and for any point x, suppose the x is a point with non-zero subgradient, then we can define this notion, this quantity called Vf of x bar semicolon x. This definition has a geometric meaning. It means that if you draw this hyperplane, so this hyperplane is H. Before we talk about the half space on this side, and this is like the boundary. The boundary is just 0. Right? Half space is less than equal to 0. If you draw this hyperplane along this point x, and the perpendicular direction is f prime is a subgradient. And now let's consider the point x bar. This this Vf is nothing but the distance from x bar to the hyperplane. Right here we are normalizing this direction, and then you are taking the inner product between the two. So this is just the distance. But this is when okay, this is when x bar is on the other side. If x bar is on this side, then you will change the sign for the inner product. It will be negative. Then it's not that meaningful. But we always only care about a point x bar on this side, because later we will use x bar as x star. So it's always positive. So it's always the distance between the point x bar or x star to the hyperplane. Okay, to make it complete, if x prime of x is 0, let me just define this quantity to be 0. Let's give this point a name. Let's call it x bar p, meaning that this is a projection of x bar onto the hyperplane. This is the same projection operator as we mentioned before. And xp can be written as so this just means from the point x bar, you go this long. You go this long means that the distance between x bar to the distance, and along which direction? That's the negative subgradient direction, right? Yes, this should be plus here. This is minus. This should be plus. Yes, should be plus. Go along this subgradient direction and with this length, then you go to the projection point. We also define, so consider again this sequence of points. This will be the search points or the iterates of your method. And we define Vi suppose this is a point x0, then this is v0, right? And if you have another hyperplane, it's here. If you have another hyperplane, then this distance will be v1, right? And we are just picking the smallest distance. So then this distance, then Vk star is also a maximum this is a point x star, and this is a distance v0, distance v1. We can also have another one, v2. So the minimum of those three v's is the v2, right? And v2 can also be viewed as the radius of the maximum ball that is contained in the set, localization set S2, right? This set just S2. And we are trying to put a ball inside of S2. And this is your ball. It's tangent to this line here. This is H0. This is H1. This is H2, right? We're trying to put a ball, the maximum ball, inside of the S2. And the maximum radius of the ball is the smallest v. Right? So this is just the claim. And so this is a way to describe how small your localization set is. This is a way to quantify, right, how small it is. It's just the smallest v we have. And hence, the subgradient method is trying to give an upper bound on this v. If you have an upper bound on the v, you can also, okay, so I'm going to show you a lemma. With that, so that lemma connects this quantity vk star with the function value gap. The minimum of all the function values. This function value gap. I think it's m times this. It's bounded by m times this. And m is the Lipschitz constant for the function f. So with this inequality, we can connect the function value gap and this quantity v. And if you have an upper bound on the v from your algorithm, because v depends on the search points xi, and they come from the algorithm, right? So if your algorithm can give you an upper bound on this v, you can also upper bound the function value gap, and hence you can derive the convergence rate and complexity. Now let's prove this inequality, how to connect the function value gap and the vk star. suppose the function f is convex and also M Lipschitz continuous on a ball centered at x bar, and also the radius is r, then we can show the function value gap is no more than m times this distance. And assuming the x here such that the distance is between 0 and r. So this is non-negative. It's on the other side of the half space. And also, with this, we can show for the iterates of your algorithm, a certain algorithm, then the minimum value of your function value of the iterates minus f star. So this gap is bounded by m times the smallest v. Okay, so here's a fact. This is a fact in the homework, and you need to show this one. The fact is, for any 2 points, for x in Q. I'm sorry, we are not that far. We are not using the constraint yet. Consider this point xp bar. Xp bar is in the hyperplane hx, right? This is hx, the hyperplane xp bar is in the hyperplane, and hence it satisfies this inequality, right? This equality is 0 if you put x bar here. This is 0. So we have fxp bar this part is just 0. So this is fx. The first inequality is because fx is no more than fxp bar, right? And the second one is just by Lipschitz continuity by the definition. And the last one is because this is a projection point. The distance between the two is just the definition, right? So we proved the first one. I think we are out of time, and we will talk about the proof of the next one next time. Any questions? So I will go through this proof again next time, both the first and second part.
So actually, I just have a slightly broader question. So we prove a lot of things in terms of Lipschitz constants and the continuity constant, so L smooth or smoothness constants. Do we generally know those for arbitrary functions?
That's a good point. Usually you do not know it. You can just have some very conservative estimate on it. So it will affect the performance of the algorithm, because the complexity for gradient method is L x0 minus x star over epsilon, right?
Right.
If you have a pro estimate, meaning that you make L pretty large than the true value, then it will make the complexity very large, right?
Right.
So it will be bad in practice. So in practice, you can always try some adaptive idea on L. So you do some tests on L. If it fails, you shrink the size of L, so it will make L close to the true value.
That makes more sense. Just because when we were talking about choosing step size in terms of L.
Yeah, it's sometimes it's an art than science.
Okay.
x 到 y 的距离，一个长度方的这样。
subdifferential 是一个 set。
对就是反正就是你用的都是只有一个，但是用哪一个呢？然后比如说那个零也可能是subgradient。
对，你就
的话，
就是假设一个 oracle， 然后这个 oracle 就 return 给你一个固定的，但是就你可能有很多个选择，那它只 return 给你一个固定的，你不用 specify 它是哪一个。
随便哪一个都可以。
对，随便哪一个都可以。但是你在你第一次 evaluate 的这个点和第二次 evaluate 这个点的时候，它会 return 给你同样的一个 value， 它不能是变的，它是只要就是 f prime of x 必须是一个固定的值，但它可以是这个 set 里面任何一个值。那你每次 evaluate 的时候必须是同样的值。
然后高频我们
周三的3个人多吗？
没人。
那我估计还好。那我在想那个。